Friends, there are like set of some important questions from electrostatics chapter, which we are going to discuss today. So let's start with the first question. The first question says that a metallic rod is placed in a uniform electric field. Select the correct options. So as you can see here, there's a rod placed in a electric field. Okay, so let's read the options here. The first option says that inside the rod there will be an induced electric field from B to A. Yeah, so that is correct here, right? Because we know like when we place a conductor in an external electric field, so we know like that there will be a induced charges, okay, which will be produced in the inner surface of the conductor, and then produce their induced electric field in opposite direction. So B to A, so that is correct. Second option, free electrons will accumulate at the end of the rod B. No, the electrons will accumulate at the end of A. Okay, not the B. The potential at end A will be more than that at B. No, again wrong, because that electrons will be at A point at end A. So that end A will be at less potential, right? Because negative potential hoga, right? And the fourth option, the electric field outside the rod will not change due to the induced charges in the rod. Yeah, that is not completely wrong. There might be some effect. Okay, so the induced charges there might be some effect in the surrounding also. So these positive charges will affect the surrounding electric field. These negative charges will affect the surrounding electric field. So that is possibility. So the most accurate option is A option. So the answer is A here. Okay, let's come to the second question here. Consider a metallic sphere of radius r concentric with another hollow metallic sphere of inner radius 2r and outer radius 3r as shown in the figure. The inner sphere is given minus q, outer plus q, the electrostatic potential. So concentric spheres we have, okay, and we need to write the electrostatic potential. This is the formula which we are going to use is the self energy, okay, plus interaction energy. Okay, so first of all, let's see the self energy. So first of all, before writing the self energy, we'll see the induced charges here. So induced charges will be like that minus q here. So here we'll have plus q, then minus q will move out. So ultimately we'll have a plus q outside. So there are three spheres we can assume here. That inner sphere, the minus q charge, that another cavity sphere which has a plus q charge, and that outer sphere which has again plus q charge. So I'm going to write the self energy first, the total self energy of all three spheres. Okay, so u1 plus u2 plus u3. What is u1? So I'm just going to use the formula here. K q square minus q square becomes q square, right, divided by 2r, because it has radius r. So that is a formula, right? First of all, that self energy of a hollow sphere is kq square by 2r, right? So r is radius of kq square by 2r plus potential self energy of that second sphere. So the charge is q, so kq square by, but radius is 2r, so it becomes 4r. And the third one, the charge is again q, to kq square by, but the radius is 3r, so it is 6r. So now if you solve these three here, okay, so like you will be getting 11 by 12 kq square by r. So it's a simple mathematics, you just solve it here. Now this is the self energy. Now we are going to calculate the interaction energy. So interaction energy will write the pairs here, because we know the interaction energy we can write with the pairs. So there are like three spheres, so obviously we'll have three pairs. So one pair is minus q and q, this one and this one. Second is plus q and q. You can see here this both the green q's, right? And the third one is minus q, the innermost and the outermost. Okay, now write the potential energy. So due to these first, so qv formula I'm going to use is q into v, so potential due to the outer one and then multiply by the charge. So k q square minus will come because there's a minus charge by 2r plus interaction energy between Q and Q, so it will be plus only K Q square by 3R, and again we'll have a minus sign K Q square by 3R. So now this is interaction energy. Now if you see that these two are cancelled, so we have this one only. So this self energy plus this interaction energy will be our answer. So kq square by r minus kq square by 2r. When you'll solve this one, you'll get 5 kq square by 12r. And if you put the k values, will be 4 will come 4, 12, 48. So option C is correct here. Okay, so hope you understood. Let's move to the next question, third question here. The third question is like related to the conducting plates. Okay, those are not at equal distance. So let's try to understand, and the plates are like grounded also. So let's try to understand the concept behind this one. So we know like when the conductor is grounded, the potential of the conductor becomes 0. Okay, in the case of conducting plates, what happens here? So what I like follow here, okay, whenever like we have a multiple plates, okay, and any plate which is grounded, so what I do here, so I'll use this thing, right? The first of all I say first of all like that we like distribute the charges, okay, with the normal method. So what is that normal method? Key like total charges 5 plus 4 9 plus q 10. So half of the total charge will be on our extreme outer surfaces, and then based on that we distribute. So let's distribute the charges first. So first distribute the charges. Okay, so I'm just going to like write the steps here. So just follow like every time when you like see this kind of question. So first distribute the charges. So total 10q to half 5q. So 5q here, 5q here. This one has q, so now we'll balance it, minus 4q plus 4q. Then q minus q, and becomes this one. Second is like whichever plate is grounded, make that charge on that plate 0. Okay, so charge on grounded plates become 0. Means the charge will go to the earth. That's what we say. That's what we can assume right now. Okay, so like because the potential will become 0, the potential. So initially that this plate, if we talk about, it has a q charge, so that means it has some potential. So when we connect it, so the potential of this plate should be 0, which is possible only when the charge on the plate is 0. Yes or no, right? So the potential, so first of all, okay, so the first step we can do is like make the charge on the plate 0. So q charge is there, so that means because of the second step, q charge will follow, will flow to the ground. Okay, now after this one, we'll see now there are two plates which are grounded. So first and third plate, so both will have a 0 0 charges now. So 0 0 0 0, and this one has 5q. Now we'll write the charges. Let's say now we need to find the final charges. So q1 q2 I'm assuming, q3 q4 I'm assuming here. Okay, and the middle plate which we have a charge 5q. Now we'll use the concept the electric field inside the conductive plate is 0. So if I take this point, let's say the p point, if I take, so electric field at p point is 0, that means that I can write this equation that q1 is equal to q2 plus 5q plus q3 plus q4. I hope you know like this equation. And similar, okay, and this q3 plus q4 is 0, so make it 0. So just okay, one second, we don't need to write this equation, just see like directly we can get it. See in the middle plate, if you see the middle plate here also, like if I take this as a point, r point, let's say, so electric field at this r point is 0. So electric field at this r point is 0, that means electric field due to this plate has to be 0, and they have 0 because they have no charge. So that means this plate, okay, 5q, okay, will produce no net electric field 0 here. That is possible only when we have an equal amount of charge on both the surfaces. Yes or no? Will the electric field has to be cancelled out. So now you see that on the middle plate, the 5q by 2 charges are present on the either side. Now with this one, we'll induce the charges and we'll calculate. So 5q by 2 will come on this side. So here, so minus 5q by 2, 5q by 2, your net charge is 0, so we have to balance it. Minus 5q by 2, 5q by 2. These are the like final charges. Now again, these are grounded, these are grounded. So the charges, so third step, find the charges, final charges on each surface of plate, and the last one, the outer surface charge of grounded plate will flow to ground. Okay, so now we have this grounded. So this one, the minus 5, so see this 5 minus 5q by 2 will not flow because of there's an attraction from this side. So only this 5q by 2 charge will flow to the ground. So the total charge, so earlier there was a q charge, now this is a 5q by 2 charge. So q plus 5q by 2, that means 7q by 2 charge will flow to the ground through S1. So 7q by 2 is not there in the option, so that means none of these is the answer. Okay, so that's like the top point, like the concept which you can use in these type of situations. Okay, so hope you understood this one. Let's move to the like next some similar type of questions, or like some important questions on this topic. Okay, let's see that another questions on this same chapter. Consider question number 4. Consider a thin conducting spherical shell of radius r having charge q. A point charge q is placed at a distance r by 3 from the center of the shell. Another point charge 2q is placed at the... Okay, so let's say so this question, so I'm solving this question here. Okay, so there's a spherical shell which has a q charge, radius is r. There's another charge q placed at r by 3 distance, and 2q charge placed at 3r distance from the center. Now they're asking like if the shell is grounded, okay, find the charge flown through the grounding wire. So there's a like concept which we can use here, when the conductor is grounded, so the potential of the conductor becomes 0. Now when the conductor of the potential of the conductor becomes 0, there is a spherical shell, so the potential of the shell will be 0. Okay, and we know one thing, whatever charge is present inside the shell, inside the cavity, okay, so it has nothing to do with the surrounding, okay, in the external field, in the external region. So here that what we can say here, that like if we distribute the charges, so q charge is inside the sphere, so it will induce a minus q charge here, plus q charge will come up. So this q and this minus q, okay, they make a system here, okay, the cavity charges. Okay, these two charges, okay, like are separated, are cut off from that space, outer region. Okay, so they have nothing to do with the anything, okay, nothing to do anything with the surrounding. Okay, so what will happen here, so to make the potential of the spherical shell 0, that will be because of the outer charges, outer surface charge, or the outer charges, the charges those are outside. Getting my point here? So these q and minus q, the inner charges, that cavity charges, okay, they will not make the potential on the spherical shell 0. Getting my point here, right? So potential of the shell is 0, means on the surface the potential is 0, right? So potential on the surface is 0, that's what it is, right? That's what we say, so who will make that potential equal to 0? The outer surface charges. Outer surface charges, like the charges, those are outside. So that's what we are going to do here. So that potential, so q plus q and 2q are there, like, so that's rounded. So let's say The net, after grounding, the final charge on the spherical shell is q dash. So net potential of this spherical shell is 0. That means k q dash by r, that self potential plus potential due to other. Other may, like, they will have only 2q. So 2q will produce that potential. So k 2q कितना potential आएगा at the center 3r is equal to 0. So यहाँ से q dash will be like minus 2q by 3. So this 2q by, अब it is coming negative. That means that extra charge has went. So q plus q charge was gone, it becomes 0. Now again 2q by 3 charge is also gone, then only it becomes negative. Getting my point here? So net charge which is gone is 2q plus q plus 2q by 3, which is q plus 5q by 3. So that is the fourth option. Clear? So that is again a good concept, good question. Question number 5th, conducting sphere of radius a has charge q on it enclosed by neutral conducting concentric spherical shell having inner ray. Okay, this question is similar to that question number 2. Okay, because after in this question number 2, the charges were like minus q and 2q here, but when we distribute the charges, you see the charges are minus q plus q and outer surface plus q. In this question they have given that one only. See, inner charges they have given q, so obviously that q will induce minus q, that minus q will go plus q. So I think like this question is similar to that one, and the answer is also same, so that you can try it. Question number 6. A thin metallic spherical shell contains a charge q over it. A point charge plus q is placed inside the shell at point t separated by distance. Okay. So now read the options. Electric field at the center due to charge over outer surface of the shell is 0. Electric field at the center due to charge over outer surface of the shell is 0. Right? So this option is wrong. Why? Because the charge which is present on the outer surface will not be uniform, because there is some disturbance from the external charges. So if it is not uniform, then the net electric field will not be 0. So this is not correct. Electric field at the center due to charge over outer surface of the shell is this one, kq by b squared. No, it will not be there, because the charge is like q minus q, and that outer surface charge will have q plus q. Okay, so it will not be kq by b square then. Electric field at the center due to charge over outer surface of the shell is right. So that is not correct. Electric potential at the center due to all the charges in space. Electric potential at the center due to all the charges. So electric potential you calculate at the center. So you can see here electric potential at the center, that will be because of that inner charges and the outer charges. So what we can say is the electric field due to q plus q at t is kq by a. Electric field due to the spherical charge, which is capital Q by r, plus kq1 by p. So that is the potential, and that option D is correct. So it's a straightforward question. Okay, let's come to the next question number 7. 3 large conducting plates ABC have placed parallel to each other shown in the figure, having charges minus q plus q0 respectively. Long time after closing the switch, as 2 particles having minus q. Okay. So here, like, first of all, 2 plates, so minus q plus q, total charge is 0. So will distribute the charges 0 0, here minus q, here plus q, here 0, here 0. So initially you can see A has a negative potential, Z 0 potential. When they are connected, so charge will flow, both will come to the same potential. Let's call that potential is Y, and B potential is X. Now you can see here that the potential difference between the plates is same, and HY. That means same potential difference is produced. Okay, same potential difference is produced. So I can say VBA. B will be at high potential, obviously. So VBA is equal to VBC. So if it is like that, so V equal to E into L. That is the electric field relation between electric field and potential. So so I'm assuming that electric field between A and B is EA, and here it is EC. So EA into D is equal to EC into 2D. So we get a relation between electric field, okay, in these two regions, EA equal to 2EC. Now we are like up C, we have a charge particles projected with some velocities. They reach to the other plates. So we just need to find the velocities so that they reach. So now it's based on the kinematics only. So acceleration is QE by M. So acceleration I can write of both the charged particles. Those are projected. Both are minus Q. First of all, one is projected in this direction, one is projected in this direction, VA, VC, like that. So acceleration charge is same, electric field is different, mass is same. So acceleration will be QEA by M, or acceleration of B is Q2 times, sorry, EA by 2. Okay, so it is half EA by 2M. Clear? So now we need to see like what should be the velocity so that they cover these respective distances. So we apply the stopping distance formula as equal to V square by 2A. So in A, the distance is D, then by 2D is equal to VA square by VC square multiplied by AC by AA. AC by A, so it is AC, right? AC by AA is 1 by 2. So see, 2 cancel, so VA by VC is coming as 1:1. So option A is correct. Okay, so that's another question from this electrostatics chapter. Let's move to the next question. Okay, question number 8. Six charges of equal magnitude plus Q minus Q arranged on the ring. PR is a path perpendicular to the axis of the ring, and R is at infinite separation from P. Okay. Amount of work done to bring a charge from R to P by RP is 0. Amount of work done to bring a... So first of all, the potential at P point is 0. You can see that charge distribution is same, and the net charge is 0. 3 plus Q, 3 minus Q. The net charge is 0, so that means potential at P will be 0. Okay. P is at same distance from each and every charge particle. So work done infinite, like we assume it's 0, so work done will be 0. So first option is correct. Net dipole moment is 0, electric field is conservative field. Net dipole moment, okay. We can see there are 3 dipole moments. One is in this direction, one in this direction, one in upward. Yeah, that is also 0. B option is correct. Amount of work done to bring a charge by R to P, RP is 0 because net dipole moment is 0, and electric field is, yeah, correct. Electric field is a conservative field only, that we see now it does not depend upon path. So question number 8, A, B, C, 3 options are correct. Next question. 6 dipoles of dipole moment P, K, kappa are arranged at corners of hexagon. Consider coordinates of P, P. Okay. A and B are like on the Z axis. Okay. So just need to imagine right now here. So let's read the option. Electric field at origin O is this one. So O is in XY plane. Okay, no problem. All the dipoles are in K cube direction. Okay, outward. So that means O is an equatorial line. So equatorial line पे electric field क्या होता है? Kp by R cube, and R is A, and times 6. Is all will have same distance A. And for all the dipoles, that O is equatorial line. So this is the electric field, but here we have root 2, so this is not correct. Chalo, fine. Direction will be obviously minus K by opposite to dipole moment, but here we are getting root 2 extra, so not correct. Potential at O is 0. Yes, O is equatorial line, and potential equatorial line is 0. Potential at A, potential at B, so that we need to find. Okay, let's talk about the A point. A point is on the Z axis, so it is outward. Okay, so you just need to imagine something here now. Sorry. So point A is at A distance. Okay, so I want you to imagine. Okay, like if I try to draw this, it will be a bit confusing then. So just imagine here, from O point, the A point is here at A distance. I'm just like trying to draw the top view, right, from like so this is Z, right, direction. So this is the point A distance, and there's a dipole. This is also a distance. So what is this distance then? Root 2a. And dipole is in this direction. This is like top view. It's not xy. It's like from the like we can say we are seeing it from the hz planes. So just try to imagine. Also all depends upon the imagination. So you can see the dipole moment is in this direction, and this is the r vector. So the angle between them is theta. So we know like the potential formula Kp cos theta by r square. So that we are going to use here. Kp cos theta is 1 by root 2 and r is root 2a. So which is 2a square. And that is because of one dipole into 6. So 3. So 3 Kp by root 2a square. And that is correct. Option C is correct. And at the B point also we will get the same thing, but yeah, that will be negative because the B point will be this side and that angle will be 135. So cos 135 is minus 1 by root 2. So it should be negative here. But we are getting positive, so that's why it is wrong. Magnitude wise both are same, right? Okay, let's move to the next and this will be the last question of this session. Initially, question number 10. Initially, two plates A and B are given charges as shown. Find the final charges on the plates after the key K is closed. Okay, just understand like there's a one concept involved. Okay, when like there's a key between two conductive plates. So what happens here? So first of all, we'll distribute the charges normally. So 3q hai, so 3q by 2, 3q by 2. Here minus q by 2, then q by 2. Here 3q by 2 minus 3q by 2. Net charge 0 है तो 3q by 2 minus 3q by 2 and then becomes 0. Now what happens here when, so this is the initial charge distribution, and now when we close the key, so these two plates will have same potential now. These two surfaces basically will be at same potential. So charge will flow high to low. Okay, so obviously B point is at high potential, तो charge flow होगा ऐसे. अब कैसे होगा, like how it will be? So all the plate, so final charge on the plates after the key. Okay, so what happens here? So you'll be seeing that once the key is closed, okay. So key is closed here. So the charge which is present on this side plus 3. So this 3q by 2 charge will move, okay, through this key. So will move from left to right. So ये 3q by 2 मिलके यहाँ जाके minus 3q by 2 से मिलेगा. Then these two charges will be cancel out. समझ इसको? So 3q by 2 will make this minus 3q by 2 0. So there will be no charge on these surfaces then. So there will be a charge 3q by 2 on this surface and then minus 3q by 2 plus 3q by 2 as it is. So the final charges will be like this. So here we have 3q by 2, then minus q by 2, q by 2, 0 0, 3q by 2, minus 3q by 2, 3q by. So these are the like final charges. Now read the options. Final charge on plate A is q. Yeah, that will be q only, right? No change in this one. Final charge on plate B is 0. No, that q by 2 is there. So this is wrong. Final charge on plate C is 3q by 2. Yes, 3q by 2 is there. Yes, correct. Final charge on plate D is 0. Yeah, total charge is 0. Yeah, so A, C, D are correct. Okay, so I hope you understood these all the questions, okay, and help you to like understand the chapter in more depth. Okay, so thanks for watching, and see, more questions will be like coming, okay, from this chapter or like from the next any other chapters. Okay, so thanks for watching. Thank you.